Welcome back everyone. So in this lecture we will be finding the voltage transfer characteristics of an amplifier that we constructed using a FET. Okay. All right. This is our basic amplifier configuration. Okay, we have some input voltage Vi and some resistance connected to the gate Rg. Well, this is the gate terminal, this is the drain terminal, and this is the source terminal. Okay, some resistance connected to the drain Rd, and some supply voltage, we will call this VDD. Okay, all right. So since this is an amplifier, we will be assuming that the FET will operate in the amplification region. All right, the FET will operate in the amplification region. So if the FET operates in the amplification region, we can replace this FET by the current source model. Okay, mind it that this can only be done if the FET is operating in the amplification region. Okay, for the other regions like in the short circuit region or the cutoff region, okay, this cannot be done. All right, so if the FET is operating in the amplification region, we can write it like this. Okay, yeah, okay, so yes, these two terminals are my VGS. Okay, so the voltage of this terminal is controlling the current ID. Okay, so let's find out the expression for the voltage VDS. Okay, this will be our output voltage, the voltage across the transistor, across these two terminals, VGS. Okay, sorry, VDS. All right, so first of all we need to find the input voltage VGS. Since there is no current in the input loop, okay, no current will flow in this loop, therefore VI will equal VGS, because there will be no drop in the resistance Rg. Okay, yeah, actually you can even exclude the resistance Rg, there will be no effect in the amplifier. All right, so VGS will be equal to Vi. Very good. Then since the FET is operating in the amplification region, ID will be equal to Gm VGS. If I put in the value of VGS, I can write this as ID equals Gm times Vi. And finally, we have to go to two steps. What will be the voltage across the resistance Rd? This will be ID times Rd. Okay, by putting in the value of Id, we can write this as VRD equals Gm Vi times Rd. Okay, and finally the voltage VDS will be our VDD minus VRD. Okay, this is our VRD. Okay. Yeah, this will be our VRD, and again putting in the value of VRD, we get VDS. Our VDS is our output voltage, so Vout equals VDD minus Gm Rd Vi. Okay, so let me just write this expression out quickly. Then the expression that we got is Vout equals minus GMRD times Vin plus VDD. Okay, simple as that. So if we plot this equation, what will be the graph? Let's plot this. Okay, this will be our input voltage, this will be our output voltage. So if the input voltage is 0, then the output voltage is at VDD, right? exactly like the case we saw in BJT. This is VDD. Alright, as the input goes higher, if we raise the input, then since this is multiplied by minus sign, alright, then the output will start to go lower. Okay, the output will decrease and finally it will hit, well, the 0 point. Okay, the output will become 0. And after the output becomes 0, can it go down any further? Well, it cannot, as we already know that the output voltage cannot be negative so after this point the output will be constantly at 0 volt. Okay, and similarly for negative input voltages, okay, what will happen for negative input voltages? For negative input voltages, as we told earlier, the FET will be cut off. So if the FET is cut off, then ID will be 0, right? ID will be 0. If ID is 0, then VRD is 0, and if VRD is 0, then VDS is equal to VDD. Okay, these two will be equal. These two things will be equal. So Vout will be constant at VDD. So for negative input voltages, Vout will be constantly at VDD. Okay, so this expression is the graph for this part. Okay, only for the straight line part. Okay, in this part, this is the cutoff part, right? This is the cutoff part of the graph. In the cutoff part, this expression is not valid. All right, this expression is not valid. Similarly, for the short circuit part, this expression is also not valid. Okay, only for this amplification part, this expression will be valid. All right, this is the short circuit part. Okay, so well, this is very similar to the BJT. So what is our amplifier voltage gain in this case? What is the amplifier voltage gain? Well, we can see what is the coefficient of VI. The coefficient of VI will be the amplifier voltage gain. In this case, this is minus GMRD. All right. So in this case, we also see that the amplifier voltage gain is negative. Therefore, this is an inverting amplifier. All right, as we saw in the BJT, the same thing is happening. In the BJT case, we also saw that that was an inverting amplifier, and in the FET case, we are also seeing that this is an inverting amplifier configuration. Okay, mind one thing, that we can also make non-inverting amplifiers using transistors, using FETs and BJTs. Okay, but the configuration that we are considering is an inverting amplifier configuration. Okay, and for the configuration that we have been using, okay, you can see, let me just draw the current source part. Okay, so in this configuration, the input terminal is between G and S. Okay, this is the input port, this is the input side, this is the input, and the output is from D and S. Okay, this is the output. So the source terminal is common between both the input and the output. So this amplifier configuration using a FET is called the common source amplifier. All right, this is the common source amplifier. In the BJT case, we called it the common emitter amplifier, and in the FET case, we are calling it the common source amplifier. Except this naming, everything is same. Okay, so we just use the same arguments and the same steps. The only difference was in the BJT, the input, the control signal was a current signal, and in the FET, the control signal is a voltage signal. Except that point, all the aspects of the FET amplifier and the BJT amplifier are exactly the same. Okay, so this graph that we drew, this is the voltage transfer characteristics of the common source amplifier. All right, just write that this is the voltage transfer characteristics of the common source amplifier. Okay, so that's about it for the different amplifier configurations and transfer characteristics of FETs and BJTs. In the next lectures, we will be talking about how these devices are constructed, how we make BJTs and how we make FETs, and up until now we had been talking about ideal FETs and ideal BJTs. Okay, we did not consider any sort of non-idealities in our explanations and analysis. Okay, so but in real life, as you saw in the case of diodes, that there are some differences between ideal diodes and real diodes. Similarly, there will also be some differences between ideal BJTs and real life BJTs and ideal FETs and real life FETs. So we will also discuss a bit about that part. Okay, so see you in the next lecture. Thank you.